Everybody. So here we're problem 4.3, where we know that a power plant produces 1 gigawatt, oops, that's 6, gigawatt of electricity at an efficiency of 40%. So the first question is, how much waste is there? Well, if we know that we have an efficiency of 40%, it means that we are getting rid of 60% of electricity we consume. We can just, honestly, solve this very easily. Say that 40 is the same stays to 1 gigawatts as 60 stays to x. So we can solve this. We do 60 times 1 gigawatt. I always write 6, I don't know why. Divided by 40. And this equals to x, which is then equals to 1.5 gigawatts. Okay, so the first cold reservoir for this plant is a river whose flow rate is 100 meters cubed per second. By how much temperature of the river will increase? Well, now we have to actually use the um, specific heat of water, and we know that Q is equals to mc delta T, or we can solve this actually a little bit better and just take this part. Actually, you know what? We know the density of water. I don't know why it doesn't do that. So density of water is, let me just look up very quickly. I don't want to say something dumb. It's about 1 kilogram per meter cubed. So now we have 100, this flow rate, I'm just going to speed for now, is equals to 100 meters cubed per second. So it means that how many kilograms are passing per second? Well, it means that the mass is equals to 100 kilograms per second of water. Okay. So now we can just plug everything in, and we know that the specific heat of water is 4186 joules per kilogram per Celsius, or Kelvin. Actually, let's call everything Kelvin. I want to have everything in the same way, or in the same, of course, way. So we know that Q is equals to 1.5 times 10 to the power of 6 watts. Sorry, no, 9 watts, because it's a gigawatt. Okay, so in order to find delta T, we can do Q divided by M times C. So we have 1.5 times 10 to the power of 9 divided by, I'll show you about it so you can see it, 1.5 times 10 to the power of 9 watts divided by, well, here will be actually joules per second, of course, divided by the mass that we're calling in seconds, so it works perfectly, 100 kilograms per second. In fact, as you can see, these two erase each other, and we end up with the perfect units, times 4,186, 4,186 joules per kilogram per Kelvin. And again, cancel this out, and we end up with Kelvin, in fact. So 1.5 times 10 to the power 9 divided by 100 times 4186 is equals to, I feel like I'm a mistake point. Oh, I feel like, oh, the density of water is not 1 kilogram per meter cubed, it is 100 kilograms per meter cubed. It means that the mass over here will be 10,000. Okay, now it makes more sense. 100. Yes. And so I feel like I made a little mistake somewhere, but I can't exactly tell where. There is a problem with that with the 10 somewhere. Oh, again, it's 1,000 kilograms. I'm making a mistake with zeros. Okay, so here we have 1 times 10 to the power of 5. I want to say yes. Okay, in fact, we do get 3.6 Kelvin, about 3.6 Kelvin, and that is our answer for part B. Now we only have part C left. So here we are asked to avoid this pollution, the reader plant could still be cooled by evaporation of river water. This is more expensive, but in some areas very preferable. At what rate must the water evaporate? Function of the river must evaporate. So we know that the latent heat to evaporate water is 2260 joules per kilogram at 100 degrees, of course. So at 100 Celsius. But we know that at room temperature, it's a little bit higher. So it's about 8% higher. So our latent heat will be 2,400 joules per gram. You can find this in previous problems. Actually, in figure 5.11, that's what I'm looking at. So joules per grams, and so we're going to take this value right here. Again, now we know that we're kicking out 1.5 times 10 to the power of 9 watts every second. So we want to see how much water we're burning per second. So times 1 second, which is equals to 1.5 times 10 to the power of 9 joules. So the mass here would be equals to so latent heat is equals I can explain this. Q will be equals to mass times latent heat. There we go. So we can rewrite this, and we say the mass is equals to Q divided by latent heat, which is equals to 1.5 times 10 to the power of 9 joules divided by latent heat, which is equals to 2,400 joules per gram. So we get 1.5 times 10 to the power of 9 divided by 2,400 is equals to 625,000 grams, which is equal to 625 kilograms of water every single second. But now we know that we have about 10 power of 5 kilograms of water per second flowing. So how much is 625 over this? So we can do this. 625 kilograms. Now, of course, we're calculating per second. So it's equals to 625 divided by 10 to the power of 5 is equals to 0.00625, which is equals to 0.625%. And that is the percentage of water that's going to be, that is the percentage of water that we're going to evaporate. It's going to evaporate every single second. or the percentage of the water is going to evaporate every single second. I was helpful.